All right, welcome everyone. Today, we're doing a deep dive into an organism that every single clinical microbiologist really needs to have on their radar, Ralstonia pickettii. All the information we're going to cover today comes from a comprehensive Gemini deep search, and as always, you can find the complete list of references in the notebook that accompanies this explainer. So, let's get into it.
Okay, let's just start with the single most critical and honestly shocking fact about Ralstonia pickettii. It can get through a 0.2 micron sterilizing filter. Just think about that for a second. Our entire system for creating sterile medical fluids is built on the assumption that those filters work. This one organism's ability to sneak through completely upends that fundamental idea, making it an incredibly deceptive and dangerous threat that's literally hiding in plain sight.
So, here's how we're going to break this down. First, we'll get to know the organism itself. Then, we'll jump into the tricky parts of actually identifying it in the lab. After that, we are going to tackle the absolute puzzle of how to treat it. And we'll wrap up with the most important part, strategies for infection prevention and control.
So first up, let's get acquainted with our adversary here, because this is way more than just some harmless bug you find in water. This thing has a serious clinical dark side.
Here's the textbook definition. It's an aerobic, gram-negative rod, and yeah, it loves moist environments like water and soil. But the reason it's so important for us is its incredible resilience. It's tough. It can survive and set up shop in hospital water systems, contaminate medical products, and that leads directly to some really nasty hospital-acquired outbreaks.
Now, you might look at this timeline and think it's just a bit of boring trivia, but it's not. It's clinically critical. This journey from Pseudomonas to Burkholderia and finally to Ralstonia is at the very heart of why this bug is so hard to identify. That close family relationship it has with the Burkholderia cepacia complex, that's the root cause of so many misidentifications in the lab.
And look at the range of trouble it can cause. It's incredibly broad. Sure, bacteremia and sepsis are what we see most often, but it can cause anything from pneumonia to endocarditis. And this creates a huge diagnostic headache for clinicians. You get a positive blood culture, so is it a true life-threatening infection or is it pseudobacteremia from a contaminated collection tube? Getting that call right is absolutely critical, especially when you're dealing with vulnerable patients in the ICU or in a neonatal unit.
So, that brings us right into the laboratory. All those characteristics we just talked about create some really big challenges for identification. This is our turf. This is where we as microbiologists have to step up and unmask the real culprit.
On the surface, these characteristics look pretty straightforward, standard stuff. But the key detail, the one that causes all the problems, is its growth speed. It can take more than 72 hours for visible colonies to pop up on blood agar. I mean, that's well past the routine incubation time for a lot of labs, which means it can be missed entirely, leading to a dangerous false negative result. And this right here, this is the main trap. This is the heart of the identification problem. The biochemical profiles of Ralstonia pickettii and the Burkholderia cepacia complex are just so similar. They overlap a ton. And that means our automated systems like the Vitek 2 can get it wrong, reporting out a Burkholderia instead. The clinical consequences of that kind of misidentification can be really serious.
So how do we get it right? Well, it's a tiered approach. You start with your presumptive ID from culture and biochemicals. And MALDI-TOF is a fantastic tool for getting a fast answer. But, and this is a huge but, its accuracy is only as good as its library. For an uncommon bug like this, the commercial databases can be a bit thin. That's why for a definitive, rock-solid ID, you have to go molecular. 16S rRNA sequencing is the gold standard that will clear up any doubt.
Okay, so you've done it. You've navigated the pitfalls and you've got a solid ID. Great job. Now the next giant hurdle slams down in front of you. How do you treat it? This is a genuine puzzle because we are pretty much fighting an uncharted enemy here.
See, this organism comes to the fight preloaded with a serious arsenal of resistance mechanisms. We're talking beta-lactamases that can even chew up carbapenems like OXA60. It's often resistant to aminoglycosides, and it's intrinsically, naturally, resistant to polymyxins like colistin. This built-in defense system immediately knocks out a whole bunch of our usual go-to antibiotics.
And here it is. This is the central, most frustrating problem when it comes to treating these infections. There are no official clinical breakpoints from EUCAST or CLSI. None. So we can run our susceptibility tests, we can get an MIC value, but what does that number actually mean for the patient? We're flying blind. It creates enormous uncertainty for the clinical team. So what do labs do? We improvise. We often turn to surrogate breakpoints, usually the ones for Pseudomonas aeruginosa. But this is a risky, unvalidated move. The PK/PD parameters, how the drug moves through the body and attacks the bug, are different for different species. So calming an isolate susceptible based on Pseudomonas data gives no guarantee of clinical success. The key takeaway here is this. If you have no other choice, you must report the MIC with a very clear disclaimer explaining the limitation.
You can see this uncertainty reflected in national guidelines, too. Take the Dutch SWAB guidelines, for example. They don't have a specific chapter on treating Ralstonia pickettii. The approach is to follow the general guidance for whatever the patient has, like sepsis, and then be ready to aggressively pivot and tailor the treatment as soon as the real susceptibility results for that specific isolate are available.
Now, if we piece together case reports and data from all over the world, a picture starts to emerge. Fluoroquinolones and trimethoprim sulfametdesoxazole tend to be the most reliable options. For really severe infections, though, combination therapy is often the way to go. And I can't stress this enough. You have to have source control. If the infection is coming from a contaminated IV line, that line has to come out. Period.
The situation gets even more intense when we're talking about kids. Treating a multi-drug-resistant Ralstonia pickettii infection in a neonate or a toddler, it forces clinicians to reach for these last-resort heavy-hitter antibiotics like tigecycline and even colistin, often in an off-label capacity. It's an incredibly high-stakes situation with very few good moves on the board.
And all of this brings us to our final, and you could argue most important section. How do we prevent these infections from ever happening? Let's talk about the containment strategy.
The single most effective strategy, the absolute cornerstone, is a robust, proactive water management program for the entire facility. Water is the main reservoir, so you have to get ahead of it. That means doing risk assessments, making sure your hot water stays hot enough to kill bugs, getting rid of those dead legs in the plumbing where water just sits and stagnates, and having a clear, actionable plan for what to do if you find contamination.
And this table really shows you the specific battlegrounds. For those so-called sterile solutions, if you have an outbreak, you have to suspect intrinsic contamination from the factory. That means quarantining and testing unopened bags of vials. In dialysis units, there's zero room for error. You have to stick to AMI standards like glue. And even simple things, like taking the aerators off the faucets in the ICU, can make a real difference.
This right here is the critical paradigm shift that has to happen. When we're investigating a cluster of Ralstonia pickettii cases, our first thought can't just be, oh, someone broke aseptic technique on the ward. Our thinking has to immediately expand to consider the very real possibility that the source is a commercially sealed, supposedly sterile product that was contaminated before it ever entered the hospital.
So, to wrap it all up, here are the 4 absolute key takeaways for your lab. Number 1, it's a stealth pathogen that breaks the basic rules of sterile filtration. 2, it's very often misidentified as Burkholderia, so molecular methods are essential. 3, therapy is a nightmare because of its built-in resistance and the fact that we have no official breakpoints. And finally, 4, prevention is all about managing your water and being deeply suspicious of your supply chain.
And that leaves us with one last, kind of unsettling thought. The whole story of Ralstonia pickettii is basically a blueprint for how a common environmental organism can suddenly become a major hospital threat. So the question we all need to be asking ourselves is, which one is next? Thank you so much for joining this explainer. If you found this helpful, please do subscribe. But even more importantly, the challenges we face with bugs like Ralstonia pickettii are best solved as a community. So share your experiences. What's your lab's approach to identifying it? What wins has your hospital had with water management? Drop it in the comments below. That collaborative knowledge is exactly how we'll stay ahead of these emerging threats.